Hey guys, it's Mr. Shrum, and I am back to finish the electromagnetic spectrum tutorial. And we're going to get into the energy of electromagnetic waves right now. So last time we talked about radio waves and how they were the longest wavelengths in the electromagnetic spectrum. And now we're going to look at how they propagate. How do these waves wave, basically? When an electric current passes through a conductor, and that conductor can be a radio transmitter, the electrons in the conductor gain energy and they begin to move back and forth rapidly or oscillate. Oscillate is another word for wave. The oscillating electrons produce both an electric field, E, and a magnetic field, which we will call B. When the oscillating electrons move, the directions of these fields and the forces they exert change constantly, propagating as a radio wave. Receiving antennas in television sets, radios, and other media pick up the radio waves. The oscillating fields cause electrons in antennas to oscillate with the same frequency, and in turn, the electrons generate an oscillating electric current in the antenna. So here we see the electric field and the magnetic field and the electron bouncing back and forth. According to quantum mechanics, electrons oscillating in an atom do not give off waves continuously. They must change energy levels to emit light. Light, like radio waves, is a form of electromagnetic radiation. Recall, electrons in an atom emit light when they move from a higher energy level to a lower energy level. The frequency of the emitted light is directly proportional to the energy given off by the electrons. The higher the energy given off by the electron transition, the higher the frequency of the emitted light. This energy is expressed by the equation E equals hf, where h represents Planck's constant. And that is a constant number, which we know is 6.626 times 10 to the negative 34th power joule seconds, which we call JS. That's how we denote it in our notation. For this lesson, you do not need to use Planck's constant, but you should understand the relationship between energy and frequency. Energy is directly proportional to frequency, no matter what type of electromagnetic radiation it happens to be. So higher frequencies, higher energy. There are three common types of light sources. We have black body radiation. That refers to the electromagnetic radiation emitted by a black body due to its temperature. A black body absorbs all the radiation incident upon it, heats up, and then re-radiates energy. The spectrum of black body radiation depends only on the body's temperature and not on the type of radiation incident upon it. When black bodies emit the radiation, they glow to a certain extent, such as burning coals, incandescent light bulbs, and the sun. The greenhouse effect is, in fact, a result of retaining Earth's black body radiation. Fluorescence is the emission of light caused by the excitation of atoms in a substance. In fluorescence, a substance absorbs light at a particular wavelength and nearly immediately emits light of longer wavelength. The emission spectrum produces discrete frequencies for specific glowing gases, such as those from a mercury vapor lamp. LED, you might have heard of that term before. That stands for light emitting diode. And these are electronic devices that give off light in specific bands of energy, which is a very efficient way to generate light. light. Now we have a lesson activity. We have a black body spectrum simulator. And in this simulation, the curve represents the radiation intensity and energy emitted with respect to the wavelength at a given temperature. For a set of given temperatures, you will determine when the peak intensity lies, where the peak intensity lies, both in terms of visible color and wavelength. Find and fill in values in the table below, and the first row has been filled for you. Here are a couple notes to help with the simulation. Drag the slider to reach the temperature listed in the first column of the table. You can also type in the temperature value in the text box above the temperature slider. You may need to use the buttons to zoom in or out on either the vertical or horizontal axis to observe the curve and the peak easily. So here we go. For example, 2640, temperature, color in which the peak lies, black, approximate wavelength 1.1 nanometer. Yeah, let's see. Yeah, so let's see. So we put it at the temperature 2640-ish. And we can see the peak is in the black section. And if we wanted to there we go. So if you ever need help with that, just auto scale it and it will show you the best view of the curve. And it looks like (1.1 nanometer, like we said. Let's try 3600. And then auto scale. Very nice. Let's try 4250. Auto scale. Okay, and you see the peak is moving now. 4700. And it's moving further and further left. And then let's do 6500. Auto scale. So it's shifted now. And I'll show you all the answers. here for part A. Part B was the relationship between the temperature and the wavelengths. What about between temperature and color? As the temperature of the system increases, the wavelength of the emitted spectrum decreases. As the temperature increases, the peak of the emitted spectrum moves from red to indigo. Was the relationship between temperature and intensity? As the temperature increases, the intensity of the emitted spectrum also increases. Part D, the sun emits radiation across a wide range of the electromagnetic spectrum, but its energy peaks in the visible spectrum. A great deal of the sun's energy is given off as visible light. So it asks you to go back and put 5900 for the temperature. What is the color of a star at this temperature? It emits light across the entire visible spectrum, but it peaks in the blue range. It will look bluer than our sun does. What conclusion can you draw about the overall radiation intensity of Earth compared with the sun? What conclusion can you draw about the peak wavelength and the type of radiation Earth mostly emits? Earth gives off much less power per square meter than the sun does. Earth's radiation peaks at about 10 micrometers, much longer than the wavelengths in the visible light spectrum. This is the infrared region. So I should be able to detect it with an infrared camera. So those were the answers for that activity. And the black body simulation demonstrated that as the temperature of a system increases, the intensity of its radiation increases. It also showed that as the temperature increases, the wavelengths of the emitted radiation get shorter, higher frequencies, because as stated before, frequency is proportional to energy. Much of the sun's radiation that reaches Earth falls in the visible light spectrum. That's why you can see it. On the other hand, Earth's radiation and the radiation from most objects on Earth, such as your own body, falls outside the visible spectrum in the infrared region, so you can't see it. In the image shown here, notice the radiation curve of an incandescent light bulb. It gives off visible light, but about 90% of the energy it emits is in the infrared region, which means these incandescent bulbs are not a very efficient way to generate visible light. So a checkpoint question, infrared waves have higher frequencies than microwaves. Which statement best compares the energy of these two types of waves? Well, higher frequency means higher energy. So that's the correct answer. It's directly proportional. All right, well, that's it for this part. And next time we'll go over visible light and finish up this lesson. But until then, have a good one, stay safe, and I will see you guys later. Bye-bye.